Good luck. We're all counting on you. But so what you're going to try and figure out is how much energy is that going to take those separate protons and neutrons and smash them together in coming up with one nucleus that has those. So let's start with this. So what you're going to do is you're going to take the sum total of all of the mass of the protons plus the sum total of all of the mass of the neutrons, and then you're going to subtract the mass of the nucleus by itself. Okay? That's what you got. Now, the question being is that you got to have the numbers. So if you look at iron, so if you come over here and you find iron, okay, and it tells you on iron 56, so you've got to come to this chart and you've got to find iron 56, and that's the mass number. It has an atomic number of 26. So on the number of protons, here's what you're going to do. You're going to take 26 times, and you have to use the exact mass of the protons. Okay? You just can't use 1, or you're just going to get 0 as your answer. You have to use these exact values. So you got the proton, which is 1.007825, and there's 26 of those. Now, here's a common mistake that's made. That's neutrons, by the way. So, are there 56 neutrons? No. How many are there?
30.
30, because that's the mass number, which is the total number of protons and neutrons. So the number of neutrons is going to be 30. So you can take 30 times 1.00, and if you want to store these numbers in your calculator, that might save you a lot of hassle. Okay? So what this number is going to give you is the total mass in atomic mass units of all of what we call the nucleons, which is a fancy word for saying all the particles inside the nucleus. That's what they're called, nucleons. So if you're going to get a number, okay, big number. Now, from that, we need to subtract out the mass of the nucleus itself after you've assembled it. And the only way you can do that is you're going to come over here and you're going to find 56, which is 55.934,940. So then you're going to take the difference in all of that, okay? Once you get that difference, but that's just your mass difference, then you need to multiply that by that value of 931.49 MeVs per atomic mass unit. This is why it has kind of these weird units, because then your atomic mass units cancel out, and then you're left with MeVs. Okay? So that's where the weird units come into play. So if you do all this, you get 492.26 MeVs. Now, if you wanted to convert that into joules, you could, but that's in MeVs. So what that's telling you is that if you take, and this door swings both ways, if you take a nucleus of iron and you split it apart, okay, it's like, okay, here class, you don't want to build an iron atom, you like to tear things apart, fine. Here's an iron nucleus, tear it apart. I want you to separate it into the protons and the neutrons. Good luck with that. But then if you did that, this is how much energy would be released in that process. Okay, that's why it's called binding energy. So this door swings both ways. That's either how much energy would be released if you split it, or how much energy it would take to take the separate protons and neutrons and smash them together, okay? Now, because you're multiplying by 931.49, which is a constant, obviously the bigger difference in the mass, the more energy that's going to be involved, okay? So there is no cute way to do this. I promise you, I'm not going to show you, oh, tomorrow you can just go through and you can just do this in one step, okay? There is no cute way to do this. And on the test, on Monday, Charles, I will give you these values. You just have to know how to use them, because that's the only way you can. If you want to store them in your calculator so that you're not typing them in every time, that's what I would do, because it's just going to make life a little bit simpler. Okay, Danny, stop the camera. Stand up for a second. We got one more time.